Hello, I'm Ahmed Midany, 37-MED, and today I'm going to introduce Qormoz, our project. It is undeniable that the handicapped people face hardships throughout their lives, specifically blind people, and one of the hardest dilemmas they face is their inability to navigate through surroundings, be it in their home, workspace, or even street. Therefore, our team came up with a unique solution, a chair-like vehicle that is able to navigate through obstacles freely with the minimum effort required, and give a sound output to the user to be able to navigate through the room. So specifying the inputs, outputs, and the components we'll be using, two proximity sensors, E18, D80, and K, and output servo motors, a buzzer, sound output, and the desired direction input will be given by the pins of the Altera, and a battery, an H-bridge, and the Altera DE10 light.
My name is Saleh Muhammad, and today we are going to discuss the hardware components and how we linked each of them with Verilog code. So the first component we are going to take a look at is the H-bridge. So let's take a closer look at the pinout of the L298N H-bridge and explain how it works. So first, we have two terminals here, which are for motor A. We have one positive terminal, which drives the positive edge of the motor, and the negative terminal. The same goes for the other motor, motor B. It has two terminals, one positive terminal and a negative terminal. Next, we have three terminals. The first is a VCC, which can go up from 5 volts to 35 volts. In our case, we use the 9 volt to go with our 9 volt battery. Also, we have a ground terminal, which we grounded all our inputs and outputs here. Next, we have a 5 volt optional input or output. We use this 5 volt as an input for our IR sensors. Now, most importantly, this H-bridge drives the motors using 4 pins. Each motor has 2 pins. One pin in the forward direction and the other pin in the backward direction. So we have forward motor A, backward motor A, then forward motor B, backward motor B. Then we connected these pins to the GPIO pins on the Altera, and we assigned these pins to using the pin assignment on Quartus light to Verilog variables.
Hello, I'm Alaa, and I'm going to tell you how this car works out. So basically, I'll start telling you about having a three wheels car. Those two wheels are connected separately to two DC motors, and they are specified how to work by the inputs of the Altera. We have a third wheel here, which is the universal 360 front wheel, which is responsible for the navigation of the car. We also have here our two proximity sensors. So we have three cases. The first case, if this sensor is cut off, this means that we have nothing in front of us, so the signal, the car will move forward. We have the other case, if this sensor sends us a signal, this means, and this one doesn't send us a signal, this tells us that we will move to the right. Moving to the right is basically done by turning on the left motor of this one, so the car would move like that. The other case and the last case we have here is that we're having this sensor also on, and we're having this sensor also on. So we will have to go to the left side. To the left side, we will have to turn on the right motor, so the car would go to the left. Basically, after going either directions, we will go back to the path that we were in, the original path, and that's it.
Hi, I'm Omar Khairy, 37-MET, and here we are again with Qormoz talking about his sensors now. We use IR infrared sensors called E18, D80, and K. They're easy to assemble, easy to use infrared sensor with a long detector distance, about 45 centimeters. They are a bit immune to any interference by direct sunlight or like light bulb lights or anything like that. It has a power supply of 5 volts, a supply current of 25 megaamperes, and a maximum load current of 100 megaamperes. Its response time is about 2 milliseconds, if not less, and it has a diameter of 17 millimeters. The sensor provides a non-constant detection. So if you can see here, if it is cut, there is an LED light, a red LED light that kind of goes on and off. The sensor is active low, so when it sees an object, it gives a digital signal of 0 to the FPGA board we're using, meaning that there's an obstacle in the distance. When I move my hand, the light bulb goes off, and it gives a digital input of 1, which means that the obstacle is no more. Thank you.
Hi everybody, I'm Mahmoud. We're back with Qormoz, and I'll be discussing with you the software part. Okay, so with Qormoz we had a lot of states to deal with. The base state is where you're moving in the forward direction, and well, there is no obstacle in your way. Okay, the first state has no additional input or output other than the output is 1001, which basically means that both wheels are moving in the forward direction operated by the motors. Okay, if the front sensor is disconnected or finds an obstacle in front of it, we go into a second state where we check whether there's an obstacle on the right or not. If there is no obstacle, Qormoz heads to the right direction, and we update registers to define the state that Qormoz is in, which is that basically he deviated to the right path other than to his original path. If an object is found on the right of Qormoz, he heads to the left direction, and the registers are updated to notify that he deviated to the left path instead of the right path or in front. Okay? When any deviation happens, a counter is started to calculate how many clock cycles did Qormoz take to his deviation. As in, let's say Qormoz turned to the left direction for 5 clock cycles, then the counter would be updated to the number 5. This counter is basically used to maintain that while Qormoz headed left 5 clock cycles, he needs to head right 5 clock cycles again, so that he could be on a parallel path to his original. Okay, so when the registers are updated, the next clock cycle, when we go to execute the always block, okay, we won't head into the state of the forward direction. We will head into a state where you have deviated from your path to the left side or right side, depending on the register. Okay. Well, and since we wanted Qormoz to return to his original path after he moved left and right, he became in a parallel position. We needed him to move right back and then left to go back to his original path. So we added 2 more counters to cancel out the original counter, which calculated the number of clock cycles to the left. We had added a clock cycle to the right, which is equal to the first counter, and another one to return it to its original path. Okay, so now that we've discussed the states of moving forward and moving left and right to avoid obstacles, there are 2 other states that we have implemented into Qormoz, which is basically to take an input as to which direction you want to move in. Okay, so we've enabled the switches on the Altera, so as to move left or right based on the desired direction of the user. Okay, and that's it for software Qormoz.
Now Qormoz is moving to its default direction, which is forward. When it hits an obstacle, it starts moving to the right. When it avoids the obstacle, it starts moving to the left to be parallel. Then it moves again to the left, calibrating to its original path, regaining its default direction of forward.